Today we're going to discuss inverse differential kinematics. Before defining this term, let's just review the problems we've been talking about. Forward kinematics relates the transformation of the end effector with respect to the base frame. In other words, given our joint angles, what is our end effector position? This is a many-to-one problem. There are many solutions for one answer. Inverse kinematics tells us, given an end effector location, what are the joint angles that we have that are necessary to position and orient our end effector? This is a one-to-many problem because one end effector location could have many solutions. Forward differential kinematics is a relationship between the velocities of the joint angles and the velocities of the end effector, and this too is a many-to-one problem. It's based on the number of degrees of freedom and the dimension of the workspace. The good news about the forward differential kinematics problem is that it's a linear map, and we all like linear mappings. The problem we're going to discuss today is the inverse differential kinematics problem. Given an end effector velocity, what are the joint velocities needed to execute that end effector velocity? In a sense, what we're going to do is we're going to invert the Jacobian matrix. What this lecture at its core is going to be about is when can we invert the Jacobian? We're going to talk a little bit about inverses. So before we talk about the linear algebra behind inverting the Jacobian, let's remind ourselves some basic linear algebra terms. So the rank of a square matrix is the dimension of the span of the columns, or is the dimension of the span of the rows. If you think of the rows as vectors, those rows, if they span m dimensions for an m by m matrix, that matrix is considered full rank. We have this nice relationship that says the rank of a matrix is equal to the rank of its transpose. So that's why if we know the columns of a matrix are full rank, then the rows of that matrix also have to be full rank because the ranks of the matrix is equal to the rank of its transpose. Now let's look at when we have a non-square matrix. So here we're going to have an m by n matrix. M is the number of rows, n is the number of columns. The rank is going to be the smaller of these two numbers. Let's define these two numbers. If the rank of A is indeed m, then we'll say A is full row rank. That means the rows span an m-dimensional space. If the rank of A is n, then we'll say it is full column rank, meaning that the columns of the matrix span an n-dimensional space. If we know that a matrix is full row rank, then the rank of AA transpose is indeed m, and this matrix AA transpose is invertible. Likewise, if a matrix is full column rank, then the rank of AA transpose equals n, and A transpose A is invertible. What you'll see is that AA transpose and A transpose A, they're going to be square matrices, where A transpose A is n by n, and AA transpose is m by m. So let's come back to the Jacobian. We've seen this three-link robot before, where theta 1 is the joint angle associated with the first joint, theta 2 and theta 3, and so forth. The Jacobian we've derived many times, and I remind you that the column of each Jacobian corresponds to what the velocity of the end effector would be if we only actuated joint 1, if we only actuated joint 2, only actuated joint 3. Or another way to think of it is the columns of the Jacobian correspond to the contributions that our corresponding joints have on the ultimate end effector velocity. So if we have our joint velocities, through the Jacobian we can infer what the end effector velocity is going to be. Here we have a 3-degree of freedom system, a 3-link system, so it makes sense that we're interested in the position as well as orientation end effector velocity. Now what we want to do is ask ourselves the inverse question. Given a desired velocity at the end effector, position and orientation, what are the three joint angle velocities that we need in order to carry out this velocity at the end effector? And for this, we're able to go and solve that problem, but it only works if the Jacobian is square and if it's full rank. So now we want to ask ourselves a different question. How can we determine the end effector velocities when our Jacobian actually is non-square? In this problem here, yes, we have the same three-link robot, but now all we care about is the translational velocity of the end effector. And that's why we have this non-square matrix. Now, to go and solve the inverse differential kinematics problem, you may think all we have to do is just invert the Jacobian and we're done, but that only works for square matrices and when those square matrices have non-zero determinant. Really what we should be saying is when those square matrices have full rank. The reason why we want to use the term full rank is because this term generalizes to non-square matrices. So let's look at the problem we want to solve. Here we have the three joint velocities, our Jacobian as described over here for this robot, and the translational velocity of the end effector. This system is underconstrained. We have more variables than equations. That means the inverse will have multiple solutions. In other words, there'll be many solutions for these joint velocities to produce a desired end effector velocity. So now, what we need to do is start with this expression and come up with a notion of what the inverse of the Jacobian is for non-square matrices. So what we're going to do is we're going to look for this matrix, for now let's call it J+, that relates us from our end effector velocity to our joint velocities. This is going to be called the pseudo-inverse. There are actually two pseudo-inverses that we should consider. One is what we'll call the under-constrained case, and the other is the over-constrained case. When you look at the under and over-constrained, you can think of it in terms of the number of equations that are available. For the under-constrained system, there are not enough equations. In other words, your number of degrees of freedom that you have control over is bigger than the dimension of your workspace, and therefore your Jacobian matrix is going to be short and fat. For the over-constrained system, there are too many equations. There are too many constraints. In other words, your workspace has a larger dimension than the number of degrees of freedom that you can command, and therefore your Jacobian matrix will be tall and skinny. When we go and solve the under-constrained problem, we have an infinity of solutions. Therefore, we have the opportunity to choose one. What we're going to do is we're going to choose the one that minimizes our control effort. In other words, we're going to search for the Q dot that minimizes the amount of energy we have to put into the arm in order to effect this workspace velocity. For the over-constrained problem, there are just too many constraints. There is no solution, so the best we can do is find the closest solution. In other words, given a desired end effector velocity, we're going to find the Q dot that allows us to move the end effector at a velocity that's closest to this desired end effector velocity. When we do this, we end up with two different kinds of pseudo-inverses. This one here is J+, and the other kind of pseudo-inverse is J hash. Notice with J+, we have this JJ transpose. We have a square matrix, which is invertible. We know that JJ transpose is full row rank because J itself was full row rank. And we determine this inverse and then multiply by J transpose. Likewise, for the over-constrained problem, we have JJ transpose, which is an invertible matrix. Because we know J is full column rank, we can invert this matrix, multiply by J transpose, and that gives us our J hash. Depending upon the system that we have, that will tell us what kind of pseudo-inverse that we're going to use. When the number of degrees of freedom equals the dimension of the workspace, in other words, when our Jacobian matrix is indeed square, then either of these pseudo-inverses actually becomes the standard J inverse, the inverse of the Jacobian. So we have over-constrained, under-constrained, and fully constrained. Here are some properties of the pseudo-inverse. And I wrote these down with respect to the J hash pseudo-inverse, but I can leave it to you as an exercise to go and compute the J plus, show these properties are also valid for the J plus pseudo-inverse. So now that we have this inverse Jacobian, it kind of gives us an opportunity to start to solve some interesting problems. So one of them is trajectory tracking. Let's say we want to have the end effector of the robot follow a path in space. What we can do is sample along this curve a sequence of points and then do a sequence of inverse kinematics operations in order to go from one point to another. Now, I think we've been together long enough as a class to know inverse kinematics problems can sometimes be quite tedious to solve. So you kind of have to ask yourself, is there another way? And there is. So instead, what we can do is compute the inverse kinematics once and get our end effector onto the trajectory. So now, at this point, we know the trajectory. We could infer a tangent to this trajectory. In other words, we can infer an instantaneous velocity that we would want our end effector to follow, and then use the inverse Jacobian to produce the joint angles that we need to carry out what that end effector velocity is. We then update our joint angles and then repeat the process. In doing so, we will move along this curve. Now, it's worth noting that at some point we are making a choice as to what our step size should be. In other words, how big should delta t be? If the curve is slowly varying, then we can get away with larger step sizes. If the curve zigzags a lot, has high curvature, then we're probably better off with smaller step sizes. And this means we'll have more inverse Jacobian mappings. So in summary, in order to find the inverse Jacobian, there are two cases. One case is the under-constrained case. Here, you have an n by m matrix where n is bigger than m. You have more columns than rows. The rank, of course, is going to be m. In other words, we're going to assume we're full row rank. Here, we use the pseudo-inverse, which is sometimes called the right pseudo-inverse, J plus. And what it does is ultimately it finds us a joint velocity that minimizes this norm here. In other words, we have an infinity of solutions since it's an under-constrained problem, so we'll pick the one that minimizes our control effort. When we do this, starting with our forward differential kinematics equation, we end up with this as our inverse differential kinematics equation. The other case is the over-constrained one. Here, the number of columns is fewer than the number of rows. In other words, we have a tall and skinny matrix. Again, we'll assume now that we're full column rank. And here we have m equations, n unknowns. The pseudo-inverse we'll use here is this J hash, which is sometimes called the left pseudo-inverse. What this pseudo-inverse does is it finds the solution that's closest to the one that we desire. Because since we have an over-constrained problem, we're not going to have a solution. Again, when we start from this forward differential kinematics mapping, the over-constrained case gives us a solution that looks like this.